let's get into this. So we're going to be talking next about what I would consider one of the core pieces of some of the building blocks for automata theory that we've been talking about up to this point. I'm going to call it this, but it must stress that it's called and manifests in several other different ways. So I'm going to be referring to it as Kleine's theorem, an attribution to Stephen Cole Kleene, and much of the theory that said logician came up with in relation to regular expressions and regular languages and regular operators. So here's the theorem. But I must stress this isn't the only way of writing out this theorem, just to be very clear. I'm only putting it in the context of what we've discussed. So a language L, I already am getting excited. A language L is regular if and only if there is a regular expression that describes L. That is, the languages described by regular expressions and finite automata are regular. Boom. So here we go. So what this theorem describes is actually a characterization of the regular languages. Now, when I first defined the regular languages to you, I said that we call a language regular if there exists a deterministic finite automaton that recognizes that language. What this theorem tells you is that actually it's also that there has to exist a regular expression that describes that language too. But also, I've also given you other equivalent formulations as well, right? We previously had proven that there exists a non-deterministic finite automaton that recognizes a language if and only if there is also a deterministic finite automaton that recognizes that same language. And we talked about also the same thing for an epsilon NFA as well. So this characterization is widely attributed as Kleine's theorem. That's what I'm referring to. So here's how generally this proof tends to go. There's several ways you can go about it, but here's the way I'm going to go about it. To prove the claim, we use the following framework. So here's the picture. So I'm going to give you the picture, and we're going to be picking up and using pieces that we've established actually in previous lectures. But there's some pieces that are missing. Those are the pieces that are missing to prove this theorem. So just as a reminder, just to kind of give you a big picture of everything we've done up to this point. So we talked about how deterministic finite automata, those recognize the regular languages, right? We also proved that these NFAs, that for every DFA there is an NFA that recognizes the same language. Likewise, we already established that for any NFA, there exists a DFA that recognizes that same language. This is something we had proven in the past. Now, this part isn't terribly relevant for our theorem here. However, that is another bridge you can cross for proving the theorem. What we're going to do instead is I'm going to be using the fact that we had shown, or at least I gave you the sketch or reasoning to prove that for any epsilon NFA, there is an equivalent DFA. we established this through the subset construction, right? We talked about the lazy subset construction where we allowed it to have the epsilon moves and we accommodated for those. So for any epsilon NFA, I could show you there's an equivalent DFA that recognizes the same language. So here's the two missing pieces. So first, the main part of this theorem involves regular languages and regular expressions. So there's two parts to this. The first one that I'll point at is that for any DFA, there is an equivalent regular expression that it describes the same language. Likewise, for any regular expression, there exists a way to construct an epsilon NFA that recognizes the same language that regular expression describes. So I describe them as the first and second. Instead, I'm going to refer to this as the first part. And the first one I described as the much trickier part of this proof. That is what I'll refer to as the second part. So you might ask all the pieces, just to kind of recap here. So here, this is characterized by the subset construction. We've already seen this. So if we have 1 and 2 in place, then what happens to establish the claim that I have up above? One way we can do it is that if I give you a regular expression, I can show you. So remember, it says the language L is regular if and only if there is a regular expression that describes L. So if we've defined that regular languages are those that are recognized by a DFA, then what I do is I take a regular expression, convert it over to an epsilon NFA, so build one, then I know how to turn it into a DFA. So since I already have established this point, then I can go from regular expression to a DFA. Then the other part of this proof is to show that there's for any DFA there exists an equivalent regular expression that describes the same language this DFA recognizes. So once you have this in place, we can establish this theorem. Is that clear, everybody? So this is what I'm characterizing as Kleene's theorem. Okay, so there's two parts to this proof. I'm going to be showing you next the first part. So to do and establish one there, I'm going to present to you something called Thompson's construction. It's very often called Thompson's construction. Sometimes it's also called McNaughton-Yamada-Thompson algorithm, named after the people that are often attributed for the discovery of said algorithm or construction, however you would like to describe it. So just as a remark, some will call this Thompson's construction. So with this, you can take any regular expression, build an epsilon NFA out of it. But I'm going to describe it within this theorem. So this will establish one part of the proof, number one that we had over there. So if language L is equal to the language of R for a regular expression R, then there is an epsilon NFA E where the language where L, so L is equal to the language of E. So that language L, so basically what I'm saying is language L is equal to the language of R. Okay, so at the heart of this proof is going to be the description of Thompson's construction, which I would argue is a fundamental algorithm should you be interested in converting regular expressions over to the finite automata. So suppose suppose language L is equal to language of R for some regular expression R. We build epsilon NFA E where L is equal to the language of my epsilon NFA E, and it has the following properties. So these two properties are going to play a very large role in how we can prove that Thompson's construction is in fact correct. So these two properties are going to be, what's that word for this? It starts with an I. Starts with an I. We use this all the time in algorithm design. When we want to establish the correctness, sometimes this is a very helpful tool. It starts with an I. We're going to have two invariants, and we've used this technique before, so I'm going to hope that you get the idea of where we're going with this. These are two properties that are going to be upheld as this construction is being played out. So watch this carefully. So E has one final state. So one final state. There are no arcs, so those are directed edges or transitions. So no arcs leaving this state. So it has one final state, but there's no arcs leaving that state. So there's no transitions out of this specific state for E. Then the reason why I deliberately use the word this state is because the final state as we construct the epsilon NFA may change. And the other one is rather important, is there are no arcs transitions, as I mentioned. The arcs are transitions. If you think of it as a directed graph, arcs are transitions toward the start state. So we're going to be now characterizing the definition that we had for a regular expression. We described it inductively. I can also think of it as a recursive definition as well. So I'm going to think about it recursively. So I'm going to describe this construction in terms of building an epsilon NFA. I'm not going to explicitly describe it in algorithmic terms. Instead, I'm going to describe it as a construction, hence why I'm referring to it in this manner. But it's going to be important that this construction has these two properties along with this one, because these are going to be very helpful for us to establish that indeed what is happening is happening. Okay. So does everybody understand the game plan? Everybody understand the game plan? So just remember, this simply means that if I give you, suppose that there's a final state, you can't have it where there's transitions leaving this final state. That can't happen. And there's only one of them. And this one is saying that there are no, like say if this is the start state, there's no transitions heading towards the start state. So we use the recursive definition of a regular expression to perform induction. So we're going to use proving with mathematical induction. Or perform induction on the regular expression R structurally. So we're doing structural induction. So if you've never seen an example like this, these are really a gem when you see them. Structurally, ensuring properties 1 and 2 hold. So You might ask where we're going with this. So naturally, I'm going to describe the construction very similar way that I would describe how we talked about a definition for like a finite automaton. So I'm going to have a basis and I'm going to have an induction part, but I'm going to embed within the description of the construction its proof. So for any little details here and there, I may omit those smaller details, but may orally only state them. So I'm just going to try to keep this concise. I normally like to go into a lot of detail, so that's why I mentioned this. So here we go. Here we go. So let's start off with the basis. So recall that there's actually 3 parts to the definition of a regular expression. So there are 3 parts to the basis of a regular expression. We build E in these cases as follows. So check this out. Check this out. So we had 3 possibilities that can happen for the basis definition of the regular expression. Do you recall what they were? We had it where are they? They are epsilon, empty language or empty set, and when we had a single symbol, right? So we're going to have corresponding epsilon NFAs for those 3 cases. So I'm going to lay them out in the same order I gave them to you when I defined the regular expression. So for the first one, which is this one, here's how I would construct the epsilon NFA. I'm going to look at it like building blocks, okay? Imagine I'm building this really epic structure, like say like an Egyptian pyramid set from Lego or something like that. Don't come after me, Lego, bro. We're talking about automata theory. But imagine you have this big, complicated Lego set. And you're right at the basis. So imagine you've decomposed the regular expression into its most fundamental parts. We're going to start at those most fundamental parts. So you imagine you have this really big construction, and as you're going down, you're building intricate these parts until you eventually get down to this case. So it's going to feel like you're building bottom up the construction. At least the way that you might do this by hand. Or you can also view it that way as well if you'd like. Like I said, induction, recursion, they are 2 sides of the same coin. So we're going to have 2 states. We're going to have the start state be this one. And then we're going to have a transition from the start state to this final state on epsilon in the first case. You'd agree with me that this would, if I gave you the empty string, would accept on the empty string, correct? Because notice that I'm in the start state, there's an epsilon move, I can go right to the final state. Next one, for the empty language or empty set. Well, all I'm going to do is I'm just going to have it where you have 2 states again. Have a start state, but no transition to the final state. It's just going to sit there. Do you agree with me that you're never going to be able to get to this final state? Yeah, you're not getting over there. There's no transitions to the final state. Now, just please remember those 2 invariants that we had in mind. So that E has 1 final state. And there are no arcs leaving this state. So notice there's never arcs going out of here, and nor are there transitions heading into this start state, okay? So please keep that in the back of your mind. So next we have the one for the symbol. I bet you could help me with this one. So again, 2 states. This is going to be the start state. Suppose it's on a symbol A, like I have over there. Suppose its symbol is called A. What should go right there for the transition? So suppose I gave you the corresponding language for this one. So design an epsilon NFA that accepts on that string. What should go right there for the transition? Just A. So you do this, so if, say if it was a different input symbol, you would just put that input symbol there. So, you might ask, what the heck is going on? So, in the first case, we have expression epsilon. We have the second case, we have expression empty language or empty set. And then this third one is the expression A. So, to accept on string A, there has to be a transition on symbol A, right? So, each of these corresponds to each one of these regular expressions. I'll let you convince yourself that the invariants are holding based on the explanation I gave you here. So far these seem rather nice and straightforward. I don't like using those phrases, but I've already given you some justification why these would be, in fact, correct. So now I'm going to provide the, I would argue, is the fun part of the construction, where this really can get out of hand if you're trying to doodle this out. So here we go. So assume the statement of the theorem. Theorem holds for the intermediate sub-expressions of the regular expression. Sub-expressions of the regular expression. So just to elaborate what that means, because that's a lot of heavy lifting that I just wrote. I just wrote there. That's a lot of heavy lifting, at least mathematically speaking. I use the M word. I use the M word. It makes a good sandwich, the mayonnaise. So let me break this down, what I mean by this. So what I'm actually saying is the language of these immediate sub-expressions. So you just got to imagine I have the regular expression. Imagine there's other operators that are occurring within the regular expression. So imagine it's being decomposed into those smaller constituent parts. That's what I'm referring to as the intermediate or immediate sub-expressions. Intermediate are all the ones that happen as you're evaluating the regular expression. That's at least one way you can think about it. Languages of these immediate sub-expressions are also languages accepted by an epsilon NFA with properties 1 and 2. So now, if you're willing to accept this step in this process, so in plain language, what this is saying is you imagine you have yourself at a given step of evaluating, or parsing or understanding the regular expression. So you imagine you have your variables and you have a regular operator in between. You imagine those two parts that have been considered up to this point that have epsilon NFAs, they indeed do. And now I want to see what happens when you build up to the next part. You think of it like a very bottom-up process. So imagine I start off at the most fundamental parts, I build up an epsilon NFA from those smaller constituent parts. Each of those intermediate steps in the process of considering the entire regular expression will each have, in those intermediate parts, an epsilon NFA. So I'm going to show you how each one of those happens, okay? So what I have to do is establish for you that if I give you two constituent immediate sub-expressions, so these are ones that you've just built epsilon NFAs for, I'm going to show you how to get the next epsilon NFA in your construction. So imagine you have like a whole bunch of these kicking around. I show you how to build the next one using a union operation, a concatenation, or a star. So that's where we're going with this. I assure you that it will make a lot, if this is a big jump for you, once we see the example, it'll hopefully clarify what's going on. Okay, here we go. So, for each regular operator, presume R and S are some smaller sub-expressions. I'll say smaller expressions wherever applicable. So akin to what I just described a moment ago when we were discussing over there. Wherever applicable. So naturally I have to go through our regular operators. So let's check out what happens. Now, rather than going through delicately writing out the arguments, I'm instead going to include them in my notes. I'm going to show you the construction, and I will verbally or orally describe to you why it's correct. And the explanation in the notes provides how you might describe this as in a proof. So the first case we're going to consider when we have a union operation between two regular expressions. So what are we going to do? So here we go. This is where I get to draw some fun pictures for you. And I must stress, the pictures are not the proof. It's just to describe to you the construction. So as I have R and S. So here's now remember, R and S by the induction hypothesis, each one has an epsilon NFA. And each one satisfies invariant 1 and invariant 2. Did you notice that, by the way I was designing the epsilon NFA in our proof, that they always had like kind of like an entry state and a leaving state or final state? Like basically there's one at it was its old final state before, now I'm going to build a bigger one. So check this out. So here we go. So whenever there's a union, we're going to have two paths. We're going to have paths. So I'm going to create a larger epsilon NFA out of those epsilon NFAs. So I'm going to build a larger epsilon NFA. So I'm going to have epsilon moves that take me to either the epsilon NFA for R or the epsilon NFA for S. And then I'm going to have a new final state. Now these are no longer final states. They were final states before, but now they're going to be states where you can leave on an epsilon move to this new final state. So notice that now the final state is this new state I've created. But now those are no longer final states. Now they're just states that you're going to leave on an epsilon move to this new final state. But now notice, as a result of doing that, we have exactly one final state. And what can you notice about the start state and the final state? What did we need to establish? We need to make sure that there's no transitions leaving the final state. That's actually why we need this final state to be the only one, right? Because this would be, there's a transition leaving that state, which would have been the original final state, right? Likewise, there are no transitions heading into this start state that I've just newly created. Did everybody see that? So now notice, I want you to think about this using the intuitions you know about for finite automata. Imagine I give you a string. For that regular expression, remember, the regular expression is a declarative way of describing which strings get accepted by, the intuition here is for the epsilon NFA, you imagine this is a string that gets accepted by the epsilon NFA. But also, you can think of it as all strings that are described by the language of the regular expression, which is the same idea, right? Well, look, you can go this way. So notice that on an epsilon move, now you have all the transitions that might happen in here for that epsilon NFA that would take you here. If it's accepted, it would be right here, right? That's what has to happen. But now we have an epsilon move that takes me right here. But please remember, there's no transitions leaving out of this state either, right? So it can't be the case that there's like some funny business where like it can go to a different state inside here and then suddenly there's a bunch of problems. No, it's because of the way the invariant operates, right? Because any string that would be described by that regular expression would be a string that gets accepted by the epsilon NFA that is described by this box. So that means that it would have to have got here and accepted for that string. But now I have an epsilon move, takes me here for free. So I can get to this state, accept. Or I could move to these states over here and do it on S. But do you notice that this actually exactly characterizes what language? Characterizes this language, right? So notice that the epsilon moves characterize an OR, akin to when we talked about epsilon, when we talk about our regular expressions, right? So notice it has a very similar parallel going on here, but so notice how the union operates like a choice, just like it does for the epsilon NFAs. So notice that variates 1 and 2 hold, and indeed, it gets you the desired language as a result. And let's consider the next one. Let's consider when we concatenate the two regular expressions. So what's this going to look like? Check this out. So next we have this. So remember, I have R and S. Remember, by the induction hypothesis, I have epsilon NFAs for R and S that satisfy the two invariants. So what I'm going to do is I'm going to take them just like two blocks. I'm just going to like connect one up to the other one. But instead of making it so they have two paths like this, two options, instead I need to force it to go through R to get over to S, right? So how am I going to do that? I'm going to make the start state of my new epsilon NFA. It's going to use the start state of R. R's epsilon NFA. Then you know that to get here, because of the invariant, it had to have been because that string belongs to the language of R, right? Otherwise, it wouldn't have accepted it, right? That's true for this epsilon NFA that I've drawn in this box, right? Well, to accept any string that would be the result of R concatenated with s as the regular expression version, that would mean that it would have to be some string that would be a part of the language of s. Well, here's an easy way to do that. You force it, you pipe it through R, then you force it on, then you allow it to, on an epsilon move, to go to the start state of s, and then you make the final state be the final state of s. So notice that I am forcing it to go through R to get over to s. But the epsilon move is what I freely use, so I don't consume any symbols for my epsilon NFA. So notice that this, as a result, gives me that. Most certainly, right? But it also maintains the two invariants. Do you see that? Notice at the start state, there's no transitions heading into the start state, because remember, that property is satisfied by the epsilon NFA of R, right? There is no transitions into the start state for R. So you know it still is held for this new epsilon NFA. And also notice that there were no transitions heading out of the final state here, because that was true for S. So we're okay for case 2. Case 3, we have R star. So suppose I give you R and I want to perform the star operation. Now, this one I love drawing because at first it just looks like some hooky dooky doodle, okay? So hooky dooky doodle, okay? So here we go. So I have R. So imagine I have the epsilon NFA for R. In this case, you have to get careful when you're proving this. I think I broke it up into 2 cases for the proof here. You'll see why in a moment. So I have R, so the epsilon NFA of R. I'm going to introduce 2 new states outside of the epsilon NFA of R. So these are going to be part of my new epsilon NFA. The final state is going to be this one. The start state is going to be this one. And what I'm going to do is as follows. Now, do you remember that the star operation allows me to pick it 0 or more times whatever is going on with that regular expression, right? So I can not do it at all, right? I can do it not at all, right? Or I could do it potentially 1 or more times, right? So I'm going to transition on epsilon. So make an epsilon move that goes to the old start state. And then I have whatever's happening in R, whatever. The final state, it should allow it to go over here, right? Because it might read the string once, the desired one, or it might read it multiple times. But this is the trick. How do I get it to do it multiple times? Well, remember, use the intuition you know about finite automata, okay? Because of the invariant, you know that there's no transitions heading out of this, what used to be the final state of this epsilon NFA. No transitions heading out of it. There's no transitions heading into this one either. This is where the invariant becomes very relevant for us, because we know this as a matter of fact when we're building the epsilon NFA, right? So, what can I do then? There's nothing heading out of here. There's nothing heading into here. That means that when I perform, I follow a pathway in here, which reads symbols, right? It reads symbols. It gets me here. In the original epsilon NFA, it would accept right here, right? It accepts right there. And now, because of the epsilon move, I can get here freely, no worries. So let's take advantage of the fact that there's no transitions heading out of this state and no transitions heading into this state. So if I want to allow it to read more occurrences of a string that would have been accepted by the epsilon NFA, I just make an epsilon move that connects from the old final state to the old start state. So in the way I describe this to you, there's 2 cases that can happen. it could be the case that you follow this pathway. In that case, this gives you when you make no choices. Versus this one, where it permits you to make one or more choices. Namely, in one case, you end up with what language? You end up with just selecting, it would be for when you have the empty string, right? Otherwise, you have it where you can get LR, concatenate with L and R. And then you can keep going like this, right? Because you can keep following that epsilon transition right here. So again, I'll leave the proofs written aspect of this argument in the notes. So, believe it or not, since we've established via our reasoning that each one of these satisfies invariants 1 and 2, and they also indeed are identifying the corresponding resulting languages that would be expected for the epsilon NFA versus the regular expression, we have completed the induction step. So I'll leave those details in the notes. And let's proceed. So all you do now is you would apply our best friend involving mathematical induction, and that would complete the proof. So now what I want to do is I want to show you an example of applying the construction now. So now that we have the key ingredient, so remember those 3 pictures over there. I normally get people to remember them. so keep them in the back of your mind, okay? So let us build an epsilon NFA from the regular expression 1 or 0 star 0. So concatenated 0, concatenated with 1 or 0. So I think this is a pretty nice example to start off with. It has a few different pieces. It has first, it has all the operations in present. So just to make things easier for us, I'm only going to indicate the final state and the start state once we're done the construction. So we got our bits and pieces here. So we got 1 or 0. So we have these 2 pieces, right? So again, like I said, I'm going to omit including the final states, but these would be the corresponding epsilon NFAs for 1, 0, and now I got to perform the union. What's the union? Remember, we create the 2 pathways with the epsilon moves. And then we have epsilon moves that leave the old final states over to this new state I've created, which would be the final state if I was finished. So next, let's proceed. So now I need to make it so that it concatenates 0 on the front. So now we got to go through this process carefully. So which box do we need? So let's go over there. Which box are we going to need? So we're going to perform a concatenation between the regular expression for 0 and the current one we have on the rightmost side. So note, because of concatenation, I'm going to do them in order from back to front, but it doesn't matter. So which one are we going to use? The first one, the second one, or the third one? It's the second one, right? Because that's concatenation here. I deliberately didn't want to show all the operations, but we're going to use the second one. So remember, it is whatever the epsilon NFA for the first one, epsilon transition into the second one's start state. So what does that look like? Well, it'll look like this, right? So that's what R would be. So this would be the this would be the epsilon NFA for R. Then we have what? We have the epsilon transition to the start state of the other epsilon NFA. So this accounts for this so far. So far, that's what the epsilon NFA would look like. Note that if I was done here, again, this would be the final state. This would be the start state. Now we got to incorporate what I have right here. So do notice how this feels very much like a bottom-up construction, because it is. It can be viewed that way. So notice that I'm making bigger and bigger epsilon NFAs. So next, notice that I have actually already made this, so I can actually use that pattern to help me do this. So check this out. This is going to be a little bit weird at first. So I'm going to actually go over to that board because I'm just going to have a little bit of fun with this. So check this out. So I already know how to deal with 1 or 0, but now I just have to put star on it, right? So I'm just going to make sure I got an idea where I'm at. So we already know how to do that part, right? So we already have the 2 disjoint, the 2 pathways with the epsilon moves like this. 1, 0, like that. We know how to do this. That's what we had before, right? For 1 or 0, like we have right there, this part. So now we got to put the star part. So we have to use the star construction that we had over there. So this is the fun one. So let's see. I need 2 new states. I have an epsilon move there, epsilon move here. Then I'm going to introduce an epsilon transition from the old final state to the old start state. And then I'm going to have an epsilon move from the new start state to this new final state for this particular part. So now we've incorporated, now we have this 1 or 0 star part. So that's it right there. Now, let's put it all together now. Now we got to concatenate what this would be with this. So check this out. So first, because I'm already at this stage, I'm going to, since I don't want to walk all the way over here again because I'm all silly like that, I'm going to make that the start state because that's going to indeed be the start state. Now, concatenation. That's the epsilon NFA for this. This is the epsilon NFA for this. I'm going to concatenate the result. Here we go. So it says that I'm supposed to put an epsilon transition from the old final state for this epsilon NFA, which is going to go over here. So I have an epsilon transition from that board to this board. And then I get over here. And this is supposed to be the final state, because that's the final state of this epsilon NFA. And there we go. So this is the resulting epsilon NFA for this regular expression applying Thompson's construction.